What if I told you that the light entering your eyes, the sound of my voice, the vibration of a guitar string, and the seismic waves racing through the Earth's crust all share the exact same mathematical DNA? You see, they exist in completely different mediums, but they are united by one elegant, sweeping equation. And today, we're going to derive the classical wave equation and understand how we do a physical interpretation of various terms in it. So let us set the stage. What we have here is a stretched string lying along the x-axis, and a transverse wave is traveling along it. As the wave passes through any small element of that string, the element moves up and down perpendicular to the direction the wave is traveling. Now, here is the key physical picture I want you to hold in your mind. Imagine zooming in on any one tiny segment of that string. I call this the microscope on the string approach. You zoom in so far that this little piece of string looks almost straight, just slightly curved like a tiny arc. Let us say this element has a small mass dm and a small length dx. And because the wave amplitude is small, we can say this element is only slightly tilted from the horizontal. And this is a crucial assumption, small amplitude. And it simplifies everything that follows. Now, let us see what forces act on this tiny element. There are two tension forces, one pulling on the right end, which we call F2, and one pulling on the left end, which we call F1. Both have a magnitude equal to the tension T in the string. But here is the important part. They do not align horizontally. The force on the right end is directed slightly upward along the tangent to the string at that point, and the force on the left end is directed slightly downward along the tangent at that end. And because of the slight curvature of the element, these two forces do not simply cancel each other. Instead, they combine to produce a net upward force that accelerates the element vertically. Now, having built the physical picture, let's get into the math. And we are going to apply Newton's second law in the y direction. That is, the net force in the y direction equals the mass of the element times its vertical acceleration. That is, F2y minus F1y equals dm times ay. And this is our starting equation for the entire derivation. Now, let's explore this equation piece by piece. So let us start with mass of our tiny element dm that can be written in terms of the string's linear mass density mu and the element's length delta x. That is, dm equals mu times dx. Next is the vertical acceleration that can be written as ay is equal to d2y upon dt2. So this tells us how fast the vertical velocity of the string element is changing at any instant. Let us now analyze the forces. So look at the right end of the element where the tension force F2 is directed along the tangent to the string at that point. And we will label the slope of the string at the right end as S2. And simple trigonometry tells us that S2 equals F2y over F2x. Now, the magnitude of the tension is T, and we can write T equals the square root of F2x squared plus F2y squared. But the small amplitude assumption tells us that the tilt here is small, and therefore F2y is much smaller than F2x, which means T, or the tension, is approximately equal to F2x. So substituting back, we get F2y is equal to tension times S2. The vertical force component at the right end equals the tension times the slope at that point. By the exact same reasoning at the left end, we get F1y is equal to tension times S1. Now we substitute everything back into Newton's second law. We replace F2y with tension times S2, F1y with tension times S1, dm with mu dx, and ay with d2y upon dt2. And we get tension times S2 minus tension times S1 is equal to mu dx times d2y upon dt2. Then dividing both sides by dx gives us S2 minus S1 upon dx is equal to mu upon tension times d2y upon dt2. Now, since the string element is very short, the two slopes S2 and S1 differ by only a tiny amount ds. So let us write this equation as ds upon dx is equal to mu upon tension t times d2y upon dt2. Well, we also know that in general, the slope s at any point is just dy over dx. So the rate of change of slope with respect to x, that is the expression you see here, can be written using this as d over dx of dy over dx. And that is the second derivative of y with respect to x. Now here is the part where we move to refining this equation further. That is, we need to switch to partial derivatives. But why so? And the answer is because y depends on both x and t simultaneously. However, here when we take the derivative with respect to x, we hold t constant. When we take the derivative with respect to t, we hold x constant. So the correct notation would be this. That is, the equation remains the same, but we qualify it with these two statements, which are basically symbolized by this curly d. Now, in the final step, you need to recall that the wave speed v on a stretched string is given by v is equal to root of tension upon mu. That gives us mu upon t equals 1 upon v square. And substituting that in over here, we arrive at the grand result that we call the wave equation. And you see, it is a surprisingly short and simple equation that governs the propagation of waves of several types. And you might think this equation only works for the sinusoidal waves we've been studying so far, but actually any function of the form y is equal to f of x minus vt or y is equal to f of x plus vt satisfies this equation. Pulses, square, triangular waves, anything. The wave equation does not care about the shape of the wave. It only cares about the relationship between how the wave curves in space and how it curves in time. And that is the deepest insight of this lesson. What started as simple force balance on a microscopic string element, F equals ma applied to a tiny vibrating piece of rope, turned into a universal law of wave physics. So you see how you can read this equation is the curvature in space is always proportional to the curvature in time. And the constant of proportionality is 1 over the wave speed squared.